Hey, this is OXDF, and today we're looking at another challenge from the HackTheBoo CTF, recently put on by HackTheBox. And today we're going to look at a pwn challenge, specifically the day one challenge, pumpkin stand. Let's go ahead and take a look at what we got. They give us both a Docker to spawn as well as some downloadables. We'll start by checking out the Docker. We can paste this IP import in here and check it out. So it looks like we have 1337 pump coins, and we can buy a shovel for that or a laser. So if we try to buy a shovel, we can only really afford one, we'll buy it. Oh, we can't buy zero. It doesn't let us buy zero. That's a good thing. Buy one and buy one. So now we have 0 pump coins left, and it says good luck crafting this huge pumpkin with a shovel. I don't know if they mean carving. Now, does it let me buy another shovel? It does actually. And it says I don't have enough pump coins, but it still seems to update my coins to be negative. So that's an interesting finding. So can we buy a laser and go negative again? How many do you want? Just buy one. Interestingly, this sends me to 0, which is kind of an interesting little exploit there. Or I don't know what the exploit, weird artifact. So if we buy another laser, how many do I want? Like 10, still at 0. Something I want to check for, what if can we buy more? Can we buy a bunch of shovels? So we buy like 10 shovels. It does send us very negative here. What happens now if we buy a laser? Still go back to 0. Interesting. One thing I want to check for to see if I can get a bunch of money is called an integer overflow, and basically it has to do with how negative numbers are stored in binary. So let's open up a new window here and do Vim. So if we take, for example, an 8-bit example. In fact, let's take an even smaller example. Let's take like a 4-bit example. So we have 4-bit numbers. So it means our possible numbers are 4-bit. So if you want to do positive integers, we do 0, 1, 2, 3, 4. So we can start to actually 1, 2, 3, 4, 1, 2, 3, 1, 1, 2, like that, 0, 0, 1, 1, and so on. Let's see, so we do like this. Supposed to be 5 would be 0, 1, 0, 1. 6 would be 0, 1, 1, 0. 7 would be 0, 1, 1, 1. Oops. 0, 1, 1, 1. And so on. In fact, let's make, for simplicity here, and for speed, so you don't have to watch me type out a bunch of stuff, we'll pretend we're dealing with a 3-bit. Oops, I did not mean to do that. Oops, I did not mean to do that. Foreground. Let's see, U to undo. Let's just get rid of just this first row. Okay, so we're dealing with 3-bit numbers. And so those are our positive integers. Now, if we want to do negative integers, what we do is we'll say, this is still 0, this is still 1, this is still 2, and this is still 3. But now we're going to say this right here is negative 1, and this is negative 2, this is negative 3, and this is negative 4. And so our values are going to go from negative 4 to 3. And what happens is, what if you add 1 to 3, you're actually going to end up with negative 4. Because of how the computer does math. And so you can actually go around, or for example, if you subtract 1 from 4, you end up with negative 4. Instead of having negative 5, you're going to have 3. And that's called an integer overflow. So I don't know if I explained that great. You can look up things called like 2's complement is the number system for what this is called. So we're going to check for that here. So we currently have 0 pump coins. If we buy, let's just say, let's find a calculator here. We buy 30 shovels. So that'll be 30 times negative 1337. We'll have that many. We should have negative 40,000. So let's do that here. We can buy 30. Oops, I guess we timed out. Let's buy a shovel. How many do we want? 30. Now, we can see right here we got back a positive number. So we clearly did and had an integer wrap here. We can test this. Our theory could be that we have a 16-bit numbers. And if it is 16-bit numbers, that means it's only going to go to negative 2 to the 15th, which is 32,000 something. And we can test that. We can add, let's see, 2 to the 16th here to this number. And that's how you can adjust it back to where it would be. And you can see that's actually the number that's close to the number we ended up with here. Because we started with 1337. So if we add 1337 to that, that's the number we have. So we started at positive 1 and we bought 30. So we really only bought 29 from 0. Anyway, hopefully that makes sense. You can see how we wrapped around. So that's interesting for sure. Can we buy a laser now? Maybe we want to. No, we're still back at 0. So Laser seems to always take all our coins. So I'm not exactly sure where to go from here, but this is why we have the source code. Let's go take a look at that. So if we look here, the downloadable gives us this folder called challenge. It has flag.txt, which we can cat, but it just has a fake flag for testing. There's a glibc directory, which has some library stuff. I'm guessing that's kind of a standard thing they get for Pwn, especially if you're going to be doing actual binary exploitation. You may end up needing to make sure your libraries are the same. And then we have this pumpkin stand thing, which is a 64-bit executable ELF, and we can run it, and it's going to be the same as the thing we had. So let's go ahead, and we're going to go ahead and open it up in Ghidra. I like to, just make a directory called Ghidra, and then if you have, download and install Ghidra, I've got, let's see, which Ghidra. So I have moved the Ghidra run script into my local bin, so I can just run Ghidra like this, and it will pop it open. I don't need this terminal anymore. And we can come here and we will create a new project, a non-shared project, in project directory HackTheBoo / let's see, we want it to be HackTheBoo, where's our Pwn, pumpkin stand, there's the Ghidra directory, and we'll call this pumpkin stand, and then we will import, cancel, and we will import into that thing our pumpkin stand binary, and it's recognizing it successfully as a 64-bit ELF. Okay, we don't need to care about this. Oops. So now we will grab pumpkin stand and drag it onto the dragon here, which will open it up in the code browser for us. Now it's going to tell us it's not been analyzed, and we're going to say yes, we will accept the defaults and analyze. Depending on the size of the binary, this can take a while, but this one's quite quick because it's pretty small. Looking at the functions, always interested to look at the main function. We also could always, this function basically is the main function. We don't have to worry about it a ton more, and it's got nicely named functions. But if we had a hard time orienting, much like in the previous reverse engineering videos, we could always do a search for strings here. And this is handy because now we can come in here and say, oh, look, here's this ASCII are getting printed, and how many do you want? And we could, here's flag.txt. Let's see, we can double click on this, and it will take us to the string flag.txt over here. And if we then right click on this, we can go to references, show references to address, and it'll show us where this string flag.txt is used. And now it actually happens that this is in main. So we got to main another way. And you can see it's actually used right here. So let's take a look at main. Anytime you see this FS offset with plus LX28, this is a canary. This is setting up to make sure that it's a stack overflow exploitation prevention technique. So we can always rename this canary and know that we probably don't have to care about it. So there's some setup, there's a banner, and we go into these nested true loops, which is kind of interesting. There's also these two things that get initialized to 0. And then after all of these loops, we open flag.txt, and it looks like we print, here's the code to get your laser, f.open, let's see, do we read? It opens the thing, let's see, we go to this. Oh, here we, it looks like we get this in, we somehow are reading this into local 48 and then printing local 40. So this would be like, rename this to flag text. We'll call this rename variable to hflag.text for handle. And so that's, so really, it looks like if we want to break out, if we want to get our flag, all we have to do is escape these, let's see, 1, 2, 3, 4 while true loops. And if we can escape them, we will win. So let's take a look. It's starting off by printing the menu, and then it says how many, then it prompts, then it scans for a, let's see, what is the string here? Oh, this is just %d. So let's rename this. So it's going to scan for a number, and it's going to store it in local 54. And we know that the first thing it asks is which one do you want? So we'll call this like item ID. And it says how many do you want? And we'll rename this variable that it scans into item num. And so if you remember, we tried to buy 0 by accident once, and if that happens, then it says you can't buy less than 1. So okay, if my item number is not greater than 0, it's going to print this, and it's going to hit this end, and it's going to come back up here and continue the loop. We actually want this to break. So as long as our item number is greater than 1, we don't hit this. Instead, we break, which puts us outside of this, puts us right here at this pump coins. So here, we're going to update our pump coins. And all we're doing is multiplying by the number of items we want to buy times, it looks like there's this table values, and we're going to take some offset into it. So it looks like if we give it item ID 1, which is the item for the shovel, we're going to go to 4. That's going to be 1 times 4, so 4 bytes after values. We'll double click on this and we'll see. It looks like values starts off as all zeros. The next one is complete. But if we can get this expanded out, not easily. But interestingly, and this is a tricky part, it's hard to see, and it's not super important, but we'll notice that if I give it the laser ID number 2, that this is going to be 8 off that, which is going to be right here, which happens to also be our variable called pump coins, which is why every time we bought a laser, we went to 0 if we bought 1 laser, because what it does is it looks up the number of pump coins we currently have, multiplies by the number we tried to buy, and subtracts it. So if no matter whether if we have -10 and we buy 1 laser, we have 0. If we have 1,000 and we buy 1 laser, we have 0, because the cost of the laser seems to be exactly whatever we have. So that's kind of interesting. Then after updating the pump coins, whether we had enough or not, it checks to see if our pump coins are greater than -1. If they are, it breaks. Otherwise, it's going to say not enough pump coins and loop back to the menu. So we want to make sure when we get here, we have more than 0 pump coins. Now, if item ID equals 1, go back around to the menu. That's interesting. So, or item ID is not equal 1. So we're going to have to buy something that is not a shovel. Now, what we didn't look at is we could buy, it looks like if we buy something at item 0, well, we'll come back to that. Okay, so we need to buy something that's not a shovel, or else we get huge, good luck. And then we need to have more than whatever this is, basically 10,000 pump coins, and or else we break. We have this problem. So we need to have a lot of pump coins. We need to buy something that's not item ID number 1. There's a few ways we can approach this. Let's go back here. We can try. Let's see. We don't need this anymore. Pumpkin stand. Let's run this. So we could buy shovels, and we already saw we could buy, if we bought a shovel here, and we bought 30, that we end up with a lot of pump coins. So now we could buy, if we buy item 0 here, we already saw that when we were over here, this will be 0 times 4, so we'll get just the thing at values, which is 0. So we're going to get the number of items we buy, which could be any number, times 0. So our pump coins are just going to stay the same. So let's come back over here and try this. So we can buy item 0, and how many do we want? 100. And we get the flag. Now it's the flag for testing. We only need to try this on the real instance, but that's one way to solve it. So let's see, come in here, let's try this again. So we started by buying our shovel. We bought 30 of them to get a bunch of pump coins. And then we bought item 0, and we bought, it doesn't matter. We'll buy 223. And interestingly, we cut off. I wonder why that happened here. Let's try that again and see if it was just a weird thing. Item 0, buy just 1 per, okay, so it worked. Let's try that one more time just to see if that was so if you buy shovel 30, and then we buy 0, how many do we want? 223, so we got the flag. It must have been some weird instance there. There's another way we can solve this, and that is, let's see, so what if we buy, what if we start with a shovel and we buy 2 of those? So now we have a nice negative number, right? Now, if we buy a laser now, we're going to, each laser is going to cost us negative that many, 13,1337. So if we buy 10 of these, we just got it, because our pump coins go from negative 1337 to basically 9 times 1337. And then we didn't buy item 1, so we get the flag again. So there's another way we can get the flag. There's probably a few more ways to approach this logically with this. The logic is pretty loose, but anyway, a couple ways to get the flag there. A neat little pwn challenge. It's neat when there's pwn that doesn't involve, heap buffer overflows and things like that, where you actually have to craft stuff. This is good beginner level stuff where you can start to play with the logic of the challenge and abuse it to sort of get to a place that you're not supposed to get. So thanks for sticking around with me to the end. Hope you enjoyed this video. If you do, please give me a like and a subscribe and all that normal YouTube-y stuff. And I'll talk to you next time. Thank you so much. Bye.